Hi everyone, welcome to my new video in my Mathematics Essentials series. In this video I will discuss one of our reciprocal trigonometric functions, y equals the cotangent of theta. Now I've drawn a theta y-axis and I have a unit circle ready to help us plot and understand the behavior of the graph. Recall that the cotangent of theta, okay, so our function is y equals the cotangent of theta, but the cotangent of theta is just equal to 1 over the tangent of theta. Alright? And that is just equal to 1 over sine theta over the cosine of theta. But that is just the same as multiplying by the reciprocal, so that's just equal to 1 times cosine of theta over the sine of theta, and this multiplication by 1 does nothing, so we just have the cosine of theta over the sine of theta. So really what we can do is just work with one of these expressions, and often the easy one to work with for graphing is this one. Okay? You'll see why. Well, I can just tell you why right now. When we're setting things equal to 0, okay, or when we're determining where the graph is undefined, it's easier to work with a quotient, right? And if you can't see that immediately, you will see it quite soon. In fact, now, pretty much. So let's start with theta intercepts. Okay, theta intercepts correspond to when y is equal to 0, but in this case, that's just the cotangent of theta equal to 0, and the cotangent of theta is equal to the cosine of theta over the sine of theta. Okay? So it's easier to work with this expression rather than 1 over the tan of theta. Okay? Now we have a quotient equal to 0, and the only way to have a quotient equal to 0 is when the numerator is equal to 0. So setting y equals 0, setting y equal to 0 just implies that the cosine of theta is equal to 0. In other words, whenever y is 0, the cosine of theta is 0. Okay? And a unit circle tells us, okay, that happens at any odd integer multiple of pi on 2. Okay? So this implies that theta is equal to n pi on 2, where n is an odd integer. Okay. The mathematical way to express this would be that n equals 2k plus 1, where k is an integer. Okay? Anywho, don't worry about that. So we have theta intercepts at all of these points where, I'll write it out, theta intercepts at any point of this form, where theta equals n pi over 2 and y equals 0. Okay? Where n is an odd integer. So the ones that are displayed on our axes, we can plot. So that's 1 pi over 2, 3 pi over 2, okay? Negative pi over 2 and y equals 0, negative 3 pi over 2 and y equals 0. So we know that the graph of y equals the cotangent of theta will intercept the theta axis at everywhere I've put down these green points. And these green points correspond to coordinates of this form. Okay, theta, these are points of the form theta, comma y, some theta value, and some comma some y value. Okay, so all of the intercepts are of this form. Okay, let's move on to y-intercepts. And y-intercepts correspond to when theta is equal to 0. So let's set theta equal to 0, because theta equals 0 just is the y-axis. Okay, but if theta takes the value 0, then there's got to be some y value equal to the cotangent of 0, okay? Because all of our values for theta have to go through the cotangent function, okay? And if 0 is just one of the values for theta, then 0 has to go through the cotangent function, okay? But y is just the output variable of the cotangent function. So there has to be some value for y equal to the cotangent of theta. That's if theta can take the value 0. And doing some manipulation, this comes down to the cosine of theta, or the cosine of 0, over the sine of 0, right? But the sine of 0 is just 0, okay? You can see that from a unit circle. Sine of 0 is just 0, so if I draw a point here and a line to it, okay, the angle between this line and the x-axis is just 0 because that line is on the x-axis, okay? So this corresponds to an angle of theta equals 0 on the unit circle. Okay, and you can also see, not that it matters, but cosine of 0 is going to equal 1. So it doesn't matter because we're going to have 0 in the denominator, which is undefined, but you could spell it out if you wanted to by writing this, all right? And then you could say is undefined, all right? And what forced our hand there? What made us do this? Because we know not to do that, okay? It was setting theta equal to 0. So setting theta equal to 0 breaks mathematics, and we shouldn't break mathematics, so we shouldn't set theta equal to 0. In other words, theta equal to 0 isn't part of the domain of the function. Theta does not take the value 0 on the graph, okay? And if theta doesn't take the value 0 and theta equals 0 just is the y-axis, well, there aren't going to be any y-intercepts. So we're going to have to make do without them. But we know that the function y equals the cotangent of theta is undefined whenever sine equals 0, because you'll have this situation, something divided by 0. So let's find the rest of the values for theta for which the graph is undefined. In other words, for which sine of theta will equal 0 and force us to divide by 0, which we can't. So for undefined values of y equals the cotangent of theta, okay, that's what we're trying to find. Well, cotangent of theta, okay, is just cosine of theta equal to the sine of theta, right? So what makes this function undefined is when sine of theta equals 0. So we have to find all the values for theta that make sine of theta equal to 0, okay? And recall that sine of theta equals 0 whenever theta equals some integer multiple of pi. Okay? So to see this geometrically, all right, whenever we're at 0 pi, sine theta equals 0, we're at 1 pi, sine theta equals 0, we go around the unit circle, 2 pi, we're back to where we were. So sine of theta is going to equal 0 again, and 3 pi. And if we headed in the opposite direction, look, from 0, where sine of 0 equals 0, sine of negative pi, so sine of negative pi is going to equal 0, sine of negative 2 pi, still going to equal 0. Okay, so any integer multiple of pi, okay, if theta takes any integer multiple of pi for its value, sine of theta is going to equal 0. Okay, so in other words, sine of m pi equals 0 for any integer m, right? Which means, this implies that y equals cotangent of theta is undefined for theta equals m pi, some integer m. Okay, you don't need to keep writing that m is an integer. I'm just trying to reiterate the fact that m is an integer. Okay, any integer, not just an even integer and an odd integer or anything, any integer multiple of pi. Okay, which means if cotangent of theta is undefined at any integer multiple of pi, okay, we have to put asymptotes in at integer multiples of pi. Okay, so let's put one in at 1 pi. Hey, please stay. Alright, let's put one in at 2 pi. Let's put one in at negative pi. So these asymptotes are just these values for theta, which make cotangent of theta undefined. Okay, our graph cannot cross these asymptotes. Okay, now we pretty much have all we need to graph the function. And consider y. Okay, and I don't mean consider y, I mean consider y, as in why this is enough to graph the function. Alright, other than just, you know, some other information which is pretty easy to get. You'll see what I mean. Okay, if we know that, let's say from this interval from theta equals 0 to theta equals pi on 2, if we know that the graph is positive here, you know what, I should indicate this as well, because 0 is a multiple of pi, so the y-axis is also an asymptote. So a graph cannot cross the y-axis. So anyways, if we're just considering this interval here, from theta equals 0 to theta equals pi on 2, okay, if we just somehow knew that the graph was above the theta axis in that interval, then we know that it would have to start somewhere up here, right? Because our graph must display asymptotic behavior, okay? But then we know that it has to intersect this point, all right? So our graph has to come away from the asymptote to intersect that point, okay? But then what does it do? Does it like just intersect the point and trend upwards towards this asymptote, or what? Okay. Another way to think about this is we need to find out whether the graph does that or does that, okay? Let's suppose it does this, okay? Then what does it do? Does it come up here, or does it turn around and go down here? Okay, because we know that we have to head towards these asymptotes. Whatever the graph does, it has to head towards these asymptotes, either side of this point, this theta intercept, okay? So in order to do that, we just find out in this interval whether the graph is above or below the theta axis. In other words, whether the y variables, or the y values, sorry, are positive or negative. And to do that, you just go to a unit circle, or more specifically, a cast diagram. So we need a cast diagram, all right? C-A-S-T. And now we look at the cotangent of theta. So I'm going to write the cotangent of theta, which is equal to, be quicker to think of it like this. In this case, 1 over tan theta, rather than cosine of theta over the sine of theta. That way we know that whenever tan is positive and negative, cotan will be the same, okay? So if tan is positive, cotan will be positive. If tan is negative, cotan will be negative, okay? Well, where is tan positive? It's positive in this quadrant, and it's positive in this quadrant, okay? Which means we could just construct a cast diagram specifically for cotan and say it's positive in these quadrants and that it's negative in these quadrants. So from theta equals 0 to pi on 2, okay, non-inclusive because 0 is undefined for cotan. Theta equals 0 makes cotan undefined. Okay, we know it's positive, all right, which means let's put an asterisk or something here, okay? Then, as we keep going, okay, we know it's negative. So, asterisk here, okay? And you can just see that it keeps changing. Positive, negative, positive, negative, positive, negative, positive, negative. So, by symmetry of the unit circle, we just know that this part of the graph is above the theta axis, and this part of the graph is below the theta axis. And if we were to go the other way around the unit circle, clockwise from the positive x-axis, the same thing will happen. Okay, it will be negative here, and it will be positive here. It will be negative here, and it will be positive here. Okay, which means we have all the information we need to graph it. Okay, that's what I meant when I said we pretty much have everything we need to graph it except one piece of information, and that's, you know, where the graph is negative and positive. But now we have that, so we can graph. So let's do it. We know that we have to intersect this point, and then we have to display asymptotic behavior either side of that point. We need to head towards this asymptote, and we need to head towards that asymptote. Okay, well, we also know that the graph is positive in this quadrant. Okay, so after the graph intersects the theta axis at theta equals pi on 2 and y equals 0, we know that since the graph is positive in this interval, it must trend upwards towards the asymptote. Okay, and since the graph is negative in this quadrant after it intersects the theta axis, it must trend towards this asymptote by heading downwards. Okay, or decreasing in y values. Now, just in case it's confusing when I'm saying, you know, this quadrant, okay, rather than this interval, they really come down to the same thing, because you can easily think of them as intervals on the theta axis or a theta number line, or like, you know, these quadrants in the unit circle. So at the moment, we can kind of use the terms quadrant or interval interchangeably. Okay, but by symmetry, okay, you see that all of the information that's displayed here is just structurally identical to the information that we've plotted here on the graph, just with different values for theta. Okay, the same thing's going to happen, and that's a consequence of the symmetry of the unit circle and our unit circle definitions for our trigonometric function. So the same thing is going to happen, and once you know what one of the curve looks like, okay, you know what the rest of the curves look like by the symmetry of the unit circle. So you're pretty much done. Okay, and now we know what the graph of the cotangent of theta looks like. We don't just know what it looks like, we know why it behaves that way. We know why there are these parts of the function that are undefined, and that's because there are these values for theta at integer multiples of pi that make cotangent of theta undefined. We know why it intercepts the theta axis at infinitely many points, and that's because at odd integer multiples of pi on 2, y will be equal to 0, and y equals 0 just is the theta axis, this axis here. Okay, so that's why we have all those intercepts. You know, we know why it's we know why the graph is always trending downwards. You know, if we're moving from left to right, the graph is always trending downwards. It's always trending downwards like this. And that's because the unit circle tells us the cotangent is positive in this interval, but then we know we have to intersect the theta axis at this point and then continue to display asymptotic behavior. Okay, so yeah, we understand the graph of the cotangent of theta pretty well. Okay, if you just focus on one of these cotangent lines and understand why it behaves that way, well, those are pretty much the same reasons why the rest of them behave that way. Okay, so if you enjoyed this video, give it a like, feel free to share it around. If anything was confusing or you'd like to ask a question, post it in the comments and I'll get back to you. If you'd like a notification when I upload a new video, subscribe to my channel. Until next time, bye for now.